Hello everyone, my name is Ibrahim Hany. I was a PhD student with Dr. Yang. I graduated last semester, fall 2020. I am currently a material and chemistry R&D engineer working at a startup developing X-ray detectors for the medical field. Today I want to showcase part of my PhD study where we reported the first demonstration of fast X-ray detectors based on the wide bandgap gallium oxide. Particularly, we based our study on iron-doped gallium oxide along the p direction. Radiation detectors are essential for many applications, for example, homeland security and the medical field. Silicon, germanium, and cadmium zinc chloride, which are the currently most commonly used materials for radiation detectors, have many limitations. Gallium oxide has very desirable properties such as its high thermal stability and its wide band gap, and in the same time it has high density. This unique combination of properties makes it a very promising X-ray detector, especially for harsh environment applications. Over the course of my PhD study, I investigated gallium oxide as an X-ray detector material, and I studied its properties, its optoelectronic properties, its point effects through a number of material experiments. In this presentation, I will only be talking about its basic characterization as an X-ray detector material. The detector we fabricated was iron-doped gallium oxide sandwiched between titanium gold electrodes. As you can see here, its resistivity was very high. It was in the order of 10 to the power 14 ohm centimeter, and this is 3 times higher than the state-of-the-art cadmium zinc chloride, which means that the leakage current of gallium oxide detectors can be significantly lower than that of cadmium zinc chloride. The band gap of iron-doped gallium oxide, as shown from tau plot here, was around 4.5 electron volts. Our fabricated device showed zero voltage operation without any applied voltage. It had signal-to-noise ratio of 140, and although this was an ohmic device, further characterization of the material suggests that such operation is due to the non-uniform iron ions distribution in the material. The signal-to-noise ratio for this device is the highest at 5 volts, at applied voltage of 5 volts. The mu tau factor, the mobility lifetime factor, was in the order of 10 to the power negative 5 centimeters squared per volt, and this value is expected to improve in the coming years. And as you can see here, at different applied voltages, its response stays fast. In our experiments, the timing resolution or the timing step was 0.3 seconds, so all of the responses at different applied voltages were lower than 0.3 seconds. In summary, we have demonstrated how promising iron-doped gallium oxide can be as a direct X-ray detector material. This was shown by demonstrating its high signal-to-noise ratio and its fast response, and at the same time its linearity between its X-ray induced current and the tube current. In the complete study, we also suggested that iron and chromium distribution can improve the optoelectronic properties of iron-doped gallium oxide, and controlling the vacancies can also minimize its polarization effect. This was a very brief presentation. For more information on that study, visit our published work, in particular this article. For any further questions or discussions, feel free to reach out to me or Dr. Gang. Thank you.